Hi, and welcome to this video lecture on reachability, controllability, stabilisability, and observability. So far, we've talked about stability and invariance, Lyapunov stability theory, and we saw how we can solve finite-horizon, linear-quadratic optimal control problems. The next step is to study infinite-horizon formulations. But to do that, we need a little interlude. We need to introduce the concepts of reachability, controllability, and stabilisability. We will start by defining the rank of a matrix. Say we have an m by n matrix A with columns A1, A2 up to An. We denote the linear space spanned by these vectors like this. This is known as the column space of A. For example, the matrix A has the columns 1, 2, 3 and 4, 5, 6. So the column space of A is the set of all linear combinations of 1, 2, 3 and 4, 5, 6. We can also look at the rows of an m by n matrix A. The linear space spanned by the rows of A is known as the row space of A. For example, this matrix has the rows 1, 4, 2, 5 and 3, 6, and its row space is the linear space spanned by these three vectors. We will not prove this, but these two spaces have the same dimension. The dimension of the column space is always equal to the dimension of the row space. This common dimension is called the rank of A and is denoted as rank A. The rank of a matrix cannot exceed any of the dimensions of the matrix. For example, a 3 by 2 matrix A cannot have a rank larger than 2. If the rank of A is equal to the highest possible value, we say that A has full rank. Two important properties of the rank of the matrix are firstly that transposition does not affect the rank, and the rank of A transpose A is equal to the rank of A. The first property is a very easy exercise, and we will prove the second one in a moment. The Rank-Nullity Theorem is one of the most important results in linear algebra. Let us start with the definition of the kernel of an m by n matrix A. The kernel of A is defined as the set of solutions of the homogeneous equation Ax equals 0. The kernel of A is a linear subspace of Rn, and its dimension is called the nullity of A. The nullity of A is denoted like this. The Rank-Nullity Theorem states that the rank of A plus the nullity of A is equal to n. Let us now prove that the rank of A transpose A is equal to the rank of A. By the Rank-Nullity Theorem, it suffices to show that the kernel of A transpose A is equal to the kernel of A. But how do we show that two sets are equal? We need to show that one is a subset of the other and vice versa. So take x in the kernel of A. By definition, Ax is equal to 0, so A transpose Ax is equal to 0. So x is in the kernel of A transpose A. We have shown that the kernel of A is a subset of the kernel of A transpose A. Conversely, take x in the kernel of A transpose A. By definition, A transpose Ax is equal to 0. Now pre-multiply with x transpose, so we have x transpose A transpose x is equal to 0. And this is precisely the squared norm of Ax, which is equal to 0. And this implies that Ax is equal to 0. Therefore, x is in the kernel of A. We have shown that the kernel of A transpose A is a subset of the kernel of A. This way, we conclude that the kernel of A transpose A is equal to the kernel of A. There is one more thing we need to know from linear algebra, and this is the Cayley-Hamilton Theorem. Now, given a square n by n matrix A, we define its characteristic polynomial as the determinant of lambda I minus A. This must be a familiar expression since this is what we use to determine the eigenvalues of A. This is a monic polynomial of degree n. The term monic means simply that the coefficient of lambda to the power n is equal to 1. This polynomial of a real or complex number lambda can be generalized to a polynomial of matrices. This is the polynomial P of a matrix X, which is given by C naught I plus C1x and so on up to x to the power n. The Cayley-Hamilton Theorem states that P evaluated at A is equal to the zero matrix. Let's see what this means. The Cayley-Hamilton Theorem states that P of A is equal to the zero matrix. In other words, C naught I plus C1a and so on and so forth plus A to the power n is equal to 0. We can now solve this equation for A to the power n. And we'll see that A to the power n is a linear combination of the matrices I, A, and so on up to A to the power n minus 1. If we multiply both sides by A, we will see that A to the power n plus 1 is also a linear combination of the same set of matrices. Inductively, we can see that all k-order powers of A, for any k at least as large as n, are linear combinations of I, A, and so on up to A to the power n minus 1. For example, for a 2 by 2 matrix, the Cayley-Hamilton theorem implies that the rank of I, A squared, A cubed, A to the power 4 is equal to the rank of IA. And with this we conclude the first part of today's lecture, and we're now ready to introduce the concepts of reachability and controllability. Consider the discrete time linear dynamical system with state xt and input ut shown here. We say that the system is reachable if there is a way to drive it from any initial state x to any final state x prime in finite time by applying some sequence of control actions u0, u1 up to un minus 1. Formally, we say that the system is reachable if for every x and x prime there is a sequence u boldface such that the state of the system at time big N starting from x and with the application of a sequence of control actions u boldface reaches x prime. Here is an example. Consider this system with two states and one input. This system, I'm telling you, is reachable. Indeed, if we take 2 points, such as x equals 1, 1, and x prime, which is 0, 0, we can apply these two control actions, and starting from x, we can reach x prime. What about these 2 points? Again, by applying these control actions, we can reach x prime from x in 2 steps. But how can we tell whether a system is reachable? To answer this question, we need to understand how the system trajectories depend on the applied inputs. We know already that for the linear system xt plus 1 is equal to axt plus but, with the initial condition x0 is equal to x, we can determine x1 from x and u0. Likewise, we can express x2 as a function of x and the control actions u0 and u1. And recursively, we see that we can determine x at time t if we know the initial state x and the sequence of control actions u0, u1, and so on up to ut minus 1. We shall now do pretty much what we did in the previous lecture to eliminate the state sequence. We define the vector u boldface subscript t to be all the control actions from time 0 to time t minus 1. Then the state of the system at time t is equal to a to the power t times x plus a matrix C subscript t times the sequence of control actions. This matrix C subscript t is defined here. Therefore, the system is reachable if and only if, for all x and x prime, there is a natural number big N and the sequence of control actions u boldface n such that x prime is equal to a to the power nx plus c subscript n times u boldface n. The question is whether such a sequence of control actions exists. We are interested in solving the equation Cn u boldface n is equal to x prime minus a to the power nx. This equation has the solution for every pair x and x prime if and only if the rank of Cn is equal to little n for some number big N. I will leave it to you to figure out why this is true, and we can discuss further in class as well. At this point, we can invoke the Cayley-Hamilton Theorem. We know that for any number big N larger than or equal to little n, a to the power n is a linear combination of a squared, and so on up to a to the power little n minus 1. Therefore, the rank of C subscript big N is equal to the rank of C subscript little n for any big N that is larger than little n. Putting it all together, we have shown that the linear system xt plus 1 is equal to axt plus but is reachable if and only if the rank of C subscript little n is equal to n. This matrix is known as the controllability matrix of the system. A linear system is reachable if and only if its controllability matrix has full rank. Let's now have a look at this example. Consider this dynamical system. We want to know whether it is reachable or not, and if it is, to find the sequence of inputs that steers the state from the initial point 1, 2, 3 to the destination minus 1, minus 2, minus 3. We start by formulating the controllability matrix of the system, which has rank 3. Next, we want to find the sequence of control inputs u0, u1, u2 that drives the system from x to x prime. This means that we need to solve this linear system, from which we can find the sequence we're looking for, and this sequence is minus 15, 23, and 10. We define the system to be reachable if we can steer its state from any initial state to any final state in finite time by applying a sequence of control actions. However, sometimes this is too much to ask. Often it suffices to be able to steer the system just towards the origin, not towards any state. We shall now introduce a weaker notion. We say that our linear discrete time system is controllable if for every state x there is a finite sequence of control actions that steers the state to the origin. If a system is reachable, it is also controllable. However, a system can be controllable but not reachable. So now let's give an example. Consider the following dynamical system with 3 states and 1 input. The controllability matrix of this system is shown here. And very clearly, its rank is 2, so the system is not reachable. However, a squared is equal to 0. Therefore, the sequence u0 is 0 and u1 is again 0 will steer any initial state x to the origin in just 2 steps. We define the system to be controllable if we can steer any state to the origin in finite time. But sometimes controllability is too much to ask for as well. Maybe our system can reach the origin only asymptotically and not in finite time. We shall now introduce a third, weaker notion. We say that our system is stabilisable if there is a controller kappa of x, such that the closed-loop system with this controller is globally exponentially stable. In fact, the system is stabilisable if and only if there is a linear feedback u equals matrix k times x, so that the closed-loop system xt plus 1 is equal to a plus bk xt is globally exponentially stable. A system can be stabilisable but not controllable. Take for example this system with 2 states and 1 input. The controllability matrix is shown here and its rank is equal to 1. Therefore, the system is not reachable. Next, we ask whether the system is controllable. We ask whether we can find u0 and u1 such that we can steer any state x0 to the origin. We hope we can find u0 and u1 that solve this equation. Equivalently, we substitute the expression for the system trajectory we gave on slide 12, substitute the problem data, and end up with a linear system of two equations. The second condition does not involve any of the inputs and can only be satisfied if x02 is equal to 0. As a result, the system is not controllable. However, using the linear feedback law U equals kx with this matrix K, we can see that the closed-loop system is stable. Therefore, we say that the system is stabilisable. In conclusion, reachability implies controllability, which implies stabilisability, but not the other way around. We conclude with the notion of observability. In this case, we consider a dynamical system of the form xt plus 1 is axt, and the system does not have an input, and we will not be focusing on the input-to-state relationship. The system has an output yt that we can measure, which is given by c times xt. Here, the problem is as follows. Suppose that x0 is unknown, and we have a finite sequence of outputs y0, y1 up to yn minus 1. The question is whether we can determine x0. We have that y0 is cx0, y1 is cax0, and so on. So we ask whether we can solve this equation to determine x0. This leads to the definition of observability. We say that this system is observable if x0 can be uniquely determined from some finite sequence of outputs. We denote by y boldface n the sequence of control actions of length n. We also define the matrix big O subscript big N, shown here. We need to solve the linear system On times x0 equals yn for x0. This system has a unique solution if and only if the rank of On is equal to little n for some number big N. Again, by the Cayley-Hamilton Theorem, the rank of O subscript k for all orders k higher than little n have the same rank. So it suffices to check whether the matrix O subscript little n has rank little n. This matrix is known as the observability matrix of the system. Here is an example. Consider this linear system. The observability matrix O3 is shown here and its rank is 3. Therefore, the system is observable. If we have 3 measurements from this system, we can determine x0. For example, suppose that we have the measurements y0 is 1, y1 is 0.5, and y2 is -1. Then, in order to determine x0, we need to solve this linear system, which yields this value of x0. And this concludes today's lecture. We revised the properties of the rank of a matrix, the Rank-Nullity Theorem, and the Cayley-Hamilton Theorem. We then defined the notions of reachability, controllability, and stabilisability for linear systems. We showed that the system is reachable if and only if its controllability matrix has full rank. And lastly, we introduced the notion of observability and showed that the system is observable if and only if its observability matrix has full rank. Thank you for watching, and see you next time.